In order to illustrate, let's consider a region in the plane. We have the x1 axis here and the x2 axis here, and in the plane we consider a region called omega. Omega is in fact a material, and inside this material we think that we have some temperature called U. And this temperature is a function of the coordinates x1 and x2. The material omega has some heat conductivity called lambda. And this function lambda is a function, of course, of the coordinates x1 and x2. Let's recall the definition of the gradient of the temperature U. We have two components in this case because we are in the plane. So in the first component we have the partial derivative of U with respect to x1, and in the second component we have the partial derivative of U with respect to x2. Note that the gradient of U is a vector which tells us the direction where the temperature is increasing the most. So that's the direction of the vector. The length of the vector tells us how much the temperature is increasing in that point. The heat velocity is denoted V vector. The heat velocity tells us how much heat which is going through a point per square meter per second. We know that the heat is going in the direction of decreasing temperature. That is in the opposite direction of the gradient of U. And this motivates why we have the following, that the heat velocity is just equal to minus the gradient of U times the heat conductivity lambda. So the heat velocity can be written in this form. The relation between the heat velocity and the gradient of U tells us that lambda measures the ability of the material to transfer heat. So if lambda has a high value, like in many materials, iron for example, metals of various kind, then lambda must be very large. It's very low for insulating materials. If there is no heat source within omega, it's possible to prove by using the divergence theorem by Gauss that the divergence of the heat velocity is equal to 0. Recall that divergence of a vector valued function can be written in this way. We have that divergence of the velocity is equal to the sum of the partial derivative of the first component of V with respect to the first spatial variable plus the partial derivative of the second component of the velocity V with respect to the second spatial coordinate x2. If we have more variables, we do it similarly. For example, if we have the spatial variable x3 in addition, we get 3 terms, and the third term is the partial derivative of v3 with respect to x3. Replacing the heat velocity v by minus lambda gradient of u, we obtain the following partial differential equation. The above description is valid for isotropic materials. In the case of anisotropic materials, we have the following relation between the gradient of U and the heat velocity. So this can be written in the following way by matrices. A matrix A, 2 times 2 matrix, which takes the following form. Note that these two off-diagonal elements always are the same. It turns out that the matrix A is a symmetric matrix, so we can write it like this. In a composite material, the conductivity matrix A is a function of the x1 and x2 variable. And for example, in a fiber reinforced material where you have fibers which are glued together like this, it could be two-dimensionally for simplicity, then the conductivity will take two different values. Associated with the conductivity matrix A, we have the effective conductivity matrix A star, which is a constant matrix. And this matrix is the matrix of a corresponding homogeneous material with the same effective properties as the composite material. For example, the thermal energy of the composite material will be equal to the thermal energy of the corresponding homogeneous material. Let us write down the expression for the thermal energy of the composite material. It's the integral over the region omega of 1/2 of the gradient of U times the matrix A gradient of U. So this is the expression for the thermal energy, and this thermal energy should be equal to the thermal energy of the corresponding homogeneous material with the same effective property. For example, the problem on the left side should have equal thermal energy as the corresponding homogeneous material on the right side, using the same boundary conditions in both problems. So these boundary conditions can be used to determine the effective parameter lambda 1 star. Using these boundary conditions, we obtain a solution U on the homogeneous material where the gradient is like this. It's 1 in the x direction and 0 in the y direction. And computing the thermal energy of this, we obtain the following problem. In this case, the gradient is constant, so computing the integral is a rather easy task. We just multiply these vectors, this constant vector, with the effective conductivity matrix, and take the scalar product with the constant vector, unit vector, and multiply with 1/2. Then we obtain, first we obtain that the matrix times the vector is just equal to lambda 1 star in the first component. In the second component, we have lambda 1 2 times 1, writing this lambda 1 2 star times 1, and taking the scalar product of these two vectors, we easily obtain lambda 1 1 star multiplied with 1/2. So computing this energy which should be equal for both the homogeneous material and for the real composite material, we are able to find the effective parameter lambda 11 star just by multiplying the energy by 2. So lambda 11 star is just equal to 2 times the thermal energy. So in order to compute the thermal energy of the real composite, we just compute it by using a numerical method like the finite element method. We can in some special cases compute it directly by using analytic methods, or we can measure it. So that's the way we compute the energy of the material and then find the effective property in the x direction, namely lambda 11 star.